Okay. So we were looking at the codecs, especially this error correcting mechanisms, right? What are the error correcting codes? So I talked about basic decoding procedure like array decoding. I talked about, you know, sphere decoding. I talked about generator matrix, parity check matrix of a code. Today I will give you first one example, and I also talked about syndrome decoding, right? So let me show you. So you know that a code can be described by either a generator matrix consisting of all the basis vectors or parity check matrix. So if generator matrix is given, we can generate all the code words by taking linear combination over the binary field when I'm talking about the binary codes. And if parity check matrix is given, then I can construct all the code, or I can look at all the vectors in the space such that hx transpose is equal to 0, right? So this is a very basic way of constructing the codes. So if you have to discover a new code, either you give us a new way of constructing the generator matrix, or you give us a new way of looking at the parity check matrix, right? So that H. So today I am going to give you the example of first code which was discovered by Hamming. Of course, he was trying to create a system of vectors which can correct single bit of error. So obviously he wanted the distance among all of them should be 3. Okay. So how he thought about it, and it's very beautiful. There are different ways you can look at it. You can look at this problem from geometrical point of view, or even a game point of view. But I'm going to describe something which is very simple. So basically, if I look at, so I suppose that length is 2. So I want to construct a parity check matrix. Okay. So in fact, length is, I'll find out what is length actually here. So I'm going to look at, I'll fix a number m. Okay. And so I'm looking at all the vectors of size m over this space. So there are 2 raised per m vectors, right? I can look at all the 2 raised per m vectors. So out of these vectors, I'm going to fill the matrix in such a way so that no 2 columns are multiples of each other. Okay. So I am going to fill this matrix in such a way from this all vectors, there are 2 raised per m vectors, such that no 2 columns are multiples of each other. Okay. So the first vector, so I think if I look at m is equal to 2, so we'll have g2 square consisting of 0, 0, 0, 1, 1, 0, 1, 1. Only 4 vectors, right? So I know that if I choose first vector 0, 0 as a first column vector, you know that singleton 0 is a dependent set, right? So we cannot use it, right? So we want independent vectors. So 0, 0 will not be there. But then I can use, so maybe 0, 1, 1, 0, 1, 1. All 3 vectors I can use, right? Because now these vectors have this property that no 2 columns are multiples of each other. If we take one column in this matrix, and you cannot find a lambda such that one vector is multiple of the other vector for any lambda over z2, 0 or 1, right? So all these 3 vectors are linearly independent. Okay, this is the key thing. So that means we are getting, for this parameter m, we are getting a matrix of size here 2 by 3, right? So if I want to increase this, so I'll go a bit further. I take m is equal to 3. So how many vectors are there in Z2, 3? 8 vectors, right? Out of these, how many vectors will be there in the matrix H? Any idea? When m is equal to 3. In case of m is equal to 2, other than 0 vector, everything was there as a column. Right? If I go to m is equal to 3, there are 8 vectors. Obviously, again, 0 vector will not be there. And what about, can I choose all of them? Because, see, if I take h is equal to, say 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0. All in Z23, there are 8 vectors. I have put all of them except 0 as a column vector. And again, this property is satisfied that no two columns are multiples of each other. Right? In fact, there is another very interesting thing that you can observe. This is a binary expansion of 1. Binary expansion of 1, right? 1, 0, 0. This is the binary expansion of 2. 0, 1, 0, right? This is the binary expansion of 4, right? This is the binary expansion of 8, right? How much? 7? Okay, yeah, 7. This is the binary expansion of 6, right? 4 plus 2, right? And this is 5. And this is 3, right? So you can also get this matrix by just writing the binary expansion of all the numbers other than 0, right? Beautiful property, right? So basically you can get this matrix in number of ways, right? So one way is we have to just make sure that the no two columns are multiples of each other over the whole space. Look at the whole space, just keep on selecting the vectors from the space and put them as a column vector and just make sure that no two columns are multiples of each other. So essentially, when you are looking at the binary case, all the non-zero distinct vectors will be part of this matrix, right? The binary case. In case of ternary case, suppose you want to construct this code over Z3 rather than Z2, then obviously there will be some repetitions. So you have to avoid, right? All vectors will not be there. Okay. So only certain number of vectors will be there. So I think I would like to invite you, as it's easy tea time problem, how many vectors will be there in case we are looking at ternary space, Z3. If we try to construct this parity check matrix over Z3, how many columns are there in the matrix? Okay, that's something for you to look at your home. Okay, so this is the parity check matrix. So this actually parity check matrix generates a code known as Hamming code. You can check that the parameters of this code is 743. So n is 7, a is 4, and d is 3. Right? And if I want to get all the vectors, c will be such that if I use this calculation, so from this parity check matrix, I can get all c by looking at this, right? Yesterday I told you, I gave you one example how to construct c out of h. So here h is this. I think it will be easy for you to construct c. You will see that how many vectors will be there in the c? No. How many vectors will be there in c? You have to see what is k here. 743. This is length. This is the dimension of the space, and distance is 3. If k is 4, then how many vectors are there? K is 4. Means there are 4 vectors in the generator matrix, right? So how many possibilities? 2 raised to power 4. 16 vectors will be there, right? 16 vectors will be there total, the whole code, right? So it's a very beautiful, interesting code. This code is also known as perfect code. It's another interesting property of this code. Now, So in general, we can construct a code of length 2 raised to power m minus 1, dimension 2 raised to power m minus 1 minus m and 3. This is your binary Hamming code. We denote it by HM. The length is 2 raised to power m minus 1. This is K and this is D. These are the general parameters. So normally whenever we are describing code, we would like to know the parameters. So this code has length 2 raised to power m minus 1. K is 2 raised to power m minus 1 minus 1. And distance is 3. Since distance is 3, it can correct single error. In fact, this code was originally used for long distance phone calls, for correcting errors. A lot of interesting applications. And nowadays, I mean, of course, in computer architecture, a lot of applications are there of this code, and some variations of Hamming code, So it's still quite useful code. Okay. So now let me show you how the decoding works for this. Okay. Now, I will show you syndrome decoding actually, okay? So now what is syndrome? You know that if X is sent, X from C is sent, and suppose Y vector is received. X is sent from C is some code, and Y is received. Then what happens? So of course, Y is, you can say that Y is nothing but X plus some error vector, right? I am assuming everything binary for simplicity, but you can of course do it, What is E? E is nothing but E1, E2, En. N bits are there, right? So basically, if x2 is say 1, then if E2 is 1, so it will be reversed. 1 plus 1 will be 0, and so on, right? This is the error vector. So what do? You just compute the syndrome of the received vector, right? That's what we usually do. So syndrome of the received vector is what? Syndrome of X plus E, right? This is nothing but HX transpose plus HE transpose. Do you agree? Linear is there, right? Linearity is there. Now, HX transpose is 0 because X belongs to C by definition. If X belongs to C, then HX transpose is 0, right? Just now you saw. Look at from here. If X belongs to C, right? So if X belongs to C, then HX transpose is equal to 0, right? So this portion is 0. So that means this is nothing but HE transpose, right? Now, if H has columns as H1, H2, so on, have n columns. Obviously, suppose E is something like 0, 1, 1. Suppose at position A, B, and C. So the error vector is like this. Some error vector, error vector is a binary vector, I am assuming, right? So some bits of 0 and 1. So at position A, we have 1. At position B, we have 1. At position C, we have 1. All other places, it is 0. So that means error has occurred at these 3 positions, right? This is the error vector. In the original X vector, X is equal to X1, X2, Xn. I am adding this error vector, E is equal to E1, E2, En. And so we are getting Y, which is Y1, Y2, Yn. Right? So at these 3 positions, A, B, C, error will occur. Now, from this formula, if I compute syndrome, so syndrome is nothing but HE transpose. That means I can say that syndrome of Y is equal to summation EI HI, where HIs are column vectors, right? Because it is HE transpose, right? So I can write it like this, which is nothing but HA plus HB plus HC. So syndrome is nothing but sum of the columns in the parity check matrix where the error occurred. Formula in the binary code. Case of binary codes, So syndrome is giving us, so if X is sent, Y is received, compute the syndrome, and syndrome will tell us which column positions, if you add, the value is this, syndrome actually. So HA plus HB plus SC, right? Right? So if there is single error, then you know that it will have only one column, right? Here we are showing you three errors. In that case, it is sum of three columns of the parity check matrix. This is the beautiful result actually, So basically, this helps you in correcting errors, right? So you know which columns. So basically, once you compute the syndrome, you can see it's a combination of which columns, right? And those columns you invert the bit because that is the position where the error occurred, right? Just invert those bits, right? So position finding is the key here, right? How to find the position where error occurred, right? By computing the syndrome, I can find out which position error has occurred. So I will inverse the bit. So now let us look at this example here. So suppose H is 001, 010, 011, 100, 101, 110, 111. This is the parity check matrix of Hamming code, right? H3. So length is 7, 4, 3. Length is 7, dimension is 4, distance is 3. Suppose some vector x is sent from the Hamming code C, which is basically Hx transpose. I can find out what are the vectors, right? Some vector is sent, and the seed vector is 1, 1, 0, 1, 0, 1, 1. Can you tell me, this is our y actually. Can you tell me what is the syndrome? So you have to compute. Syndrome of y is Hy transpose, right? H is given. Can you tell me what is y? So what is the syndrome actually? H is this, and y is this, right? Hy of, you remember that 1 plus 1 is 0, all those things are there, right? 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, right? What is the syndrome vector? Which column are you getting in the parity check matrix? I mean, you can do manually also. See, if you look at this vector and multiply with the first vector, so 0, 0, 0, 1 will be contributed from there, and 1. So what will be the first vector? First bit will be there. What will be the first bit? 1. What is the second bit? 1. What is the third bit? 0. So you computed this is the column. Which column? Sixth column, right? So we have got the sixth column. That means we know that sixth bit is corrupted, right? So you just invert the sixth bit in the received vector. So the x will be what? 1, 1, 0, 1. Right? This will be our x. Because I have inverted sixth bit. This one will become 0. Because at this position, error has occurred, right? I've shown you some idea how the code is used using the syndrome decoding to correct the errors. And I gave you one example of code, which is known as Hamming code. Clear? Any question? Clear? Now, one thing that is a challenging thing is always we want what is known as main coding theory problem. It's kind of optimization problem. See, what we want, we don't want we want to correct as many errors as possible, right? That is our goal, as many errors as possible. Or also we want to do a lot of, we want more and more code words. So it's a kind of conflicting goal. So we want maximum k and maximum d for a given n, or so basically for these parameters n, k, d. So we want to optimize these parameters, right? So that we can pack more and more information into the space, right? So what we can do, so basically many times if n and k is given, I want to find a code with maximum d. Okay, so there may be many subspaces basically for given n and given. So what I'm saying that, for example, if n is 7 and k is equal to 4, there will be one code which we have shown to you with distance 3. Maybe there is another code with more distance. We need to check what is the best possible distance for that subspace, right? So this is an optimization problem. So how do we solve it? There are different ways. People try to calculate the rate of the code. What is rate of the code? So rate of the, in fact, linear code is k by n. K is the dimension and n is the length. And normally rate lies between 0 and 1, right? Because k is less than n, right? So that means we want higher rate code. That will be better for us. This is an estimate. So we want, from engineering perspective, code will be very good if rate is close to 1, right? It's as good as, right? It's 0.99, it's very good code, right? So we want better code. So normally, it's very conflicting parameter. As soon as you want to have more rate, you have to give away something, right? So so you have to optimize that. You want to more and more distance as well, so that you can correct more errors. So it's kind of really interesting thing to look at. So people have created tables. So I can maybe show you certain tables here. So codetables.de. So you can clearly see here there are linear codes, quantum codes, and so on. So I can just click on the linear code. I hope it's working here. Yeah. So suppose I enter n is equal to 5 and k is equal to 2. I want to find out what is the best d possible. So I can just check the lookup. It is showing the best d is 3. Upper bound, lower bound is 3. So and how do we construct this code? There are ways to construct. The reference is given here, right? So for given n and given k, what is the best d possible? In small case is easy. Higher cases, still there are many open problems. Okay, what is the best way to construct a code which is having? Nowadays we have supercomputer, this and that, and now parallel computing, but all is you cannot do. The problem is finding good code is very difficult problem. All your high performance computing or the CUDA environment is not really much useful here, right? The problem is very difficult actually. Okay, so of course there is, if you are more interested in from computer science perspective, there are papers which will talk about why this problem is difficult to find that space which is having very good D, right? So this is this table you can use. In fact, I can show you. Right now I have shown you a small example, but I can show you full table also for binary case. Say for example, you see for given n and k. Now you can see that we know what is the maximum D. For all these cases, we know the answer. What is the best possible D, right? And if you go a bit down, you see there are gaps. 11 to 12, 10, 11. Which one is better? We don't know. This is open problem for you. Those who want to write research papers, it's easy thing. Can you construct a code by programming, by some construction, by some beautiful idea somewhere? If you can construct a code, so lower bound will be improved, right? So you have thing. And these upper bounds are obtained by, so there are certain ways. Like for example, sphere packing bound, singleton bound. There are different kind of bounds available on these parameters of NKD, right? So Gilbert-Washburn bound. These bounds tells you what is the upper size, right? So, and if you construct a code, so lower bound will be there. Once lower bound meets upper bound, that's the optimal code. So the search is always for an optimal code, the best possible way, right? So that you can correct as many errors as possible, right? And you can pack more space here. So all these things are open. See, 16, 17, you know, so length up to 44. And you can clearly see here, this gap increases more and more, you see here now, right? So for length, these lengths are quite open, you know. Everything is a research paper. You take one bound and fill it or improve it, there is a research paper, right? Simple. 1 page or 2 page or 3 page. You just choose the, you know, choose the area, choose the parameters, and see if you can construct. How to construct, that is your, I mean, you have to use your brain somehow, and you know, you will see that interesting thing, right? So you can clearly see the lower side is people have found, but the upper side, you know, things are still open. All, you know, this is all about bounds, actually, right? So we want a good rate code, as I mentioned. So rate is nothing but, for the linear code, rate is nothing but k by n. Okay, so we want a good code, good rate code always, right? So, so this is all about you know, basic coding theory. Now I'll show you one more thing. So I have talked about distance. So how to correct errors using distance, right? So there is an equivalent concept. So in fact, I will take a very specific example known as binary symmetric channel. What is binary symmetric channel? I am sending a vector x of 0 and 1 bits. Certain bits I am sending. Certain bits are received. So I'm assuming that the channel is flipping the bits with certain probability. Okay. 0 will become 1 with probability p, or 1 will become 0 with probability, you know, p, and 0 will remain 0 with probability 1 minus p. 1 will remain 1 with probability 1 minus p. So this kind of channel is known as binary symmetric channel, right? If you look at this binary symmetric channel, so how probabilistic decoding is done, that I will show you now. Okay, so how we can do that probabilistic decoding. Okay, so yes, so I am again taking that same example. Our repetition code, 0 is repeated 3 times and 1 is repeated 3 times. So C is 0, 0, 0, 1, 1, 1. Okay, and so generator matrix is singleton 1, 1, so that 1, 1, 1 vector, right? Parameters are length is 3, dimension is 1, and distance is 3. Distance is 3, so it can correct one error, right? So actually both Hamming code, which I talked about, and this code, these codes are very, very beautiful code, because they are you know, they are meeting sphere packing bounds, so they are perfect code actually. And there are only three examples of codes which are perfect: repetition code, Hamming code, and Gole code. And surprisingly, all these beautiful things are connected always, you know. So something is beautiful here, you know, you can find a way to construct some other beautiful thing, right? So there are mappings and ways and so on. Anyway, so our binary symmetric channel is, so it's a flipping the bits, right? So 0 is there, we get 1 with probability p. So probability of error is p, right? And if there is 1, you will get 0 with probability p. 0 to 0 will be probability 1 minus p, and 1 to 1 is probability 1 minus p, right? Right. So now, for calculations, I am assuming that normally it is assumed that probability lies between 0 and 1, 0 and half. If it is not the case, you can, you know, interchange the role of 0 and 1, but so that is our assumption, that 0 is less than or equal. So p lies between 0 and half, probability between 0 and half. Okay. So now, you know, suppose received vector is 1, 1, 0. Okay. Suppose received vector is 1, 1, 0, and probability is 0.05. Suppose, just an example, suppose probability p is 0.05 and received vector is 1, 1, 0. So now I can calculate this probability. So 1, 1, 0 is received and 0, 0, 0 is sent. What is the probability of this case, this scenario? Okay, that 1, 1, 0 is received. Received vector is 1, 1, 0 anyway, and 0, 0, 0 is sent. So in this case, I can compute individual probability, right? So probability of receiving 1 and 0 is sent, and 0 is received, 0 is sent twice. I mean, so this is twice actually. Yeah, 110 is repeated. So probability of 1 received, 0 is sent times 1 received, 0 is sent times probability 0 is sent and 0 is received. Right? So what is this probability? I can calculate this value by substituting p is equal to 0.05 and using this between 0 to 0 and 1 to 1, 1 minus p, and 0 to 1, 1 to 0 p. I can calculate this value turns out to be 0.002375. Okay. I mean, you can do these calculations. So probability is there, right? Now, similarly, the other case, received vector is 110, and when 111 was sent, I can compute the probability is this. So this probability is certainly bigger than this probability, right? So that means 111 is more likely was sent. So probabilistic decoding you can also do. This is also quite useful. I've shown you in this scenario. So basically the previous decoding method that I told you is known as distance decoding, okay, or maximum likelihood decoding, and that is same thing as this kind of decoding, the probabilistic decoding, right? So they are, you can show their equivalence, right? So you can use probabilistic decoding or that kind of decoding for, So I gave you just a couple of ideas, plenty of literature. I think maybe there are 500, 600 books on coding theory, in different directions altogether. And coding theory is sister of cryptography. A lot of deep impact on cryptography because of coding theory. So all those things are really connected. So I think I would say that up to this much only I will cover a few more things about cyclic codes briefly. I'll give an idea, and then others you can look at the the YouTube lectures. So there are about 20 lectures on coding theory in details, right? If you want to look at, but I think this much will be so. I'll talk about briefly about the cyclic code as well, and I think that's all. Then I will go and look at the actual codecs that are used in DNA storage, right? I will the way they are discovered. I will show you how things are used in different ways, right? So I think I already showed you one which was used by George Church, right? Sorry, the Nick Goldman. George Church has not used anything initially. And then after that, there was paper by Nick Goldman and Emil, so they have used this different coding technique. So, and then of course, we have shown our Gole code thing, So now, let us take an example now. So basically, I'm going to give you some idea about cyclic code and why these are good. Almost all good codes are cyclic, actually. I can say that almost all good codes are cyclic. So the popular ones like Hamming code is cyclic, the one which I have shown to you. Okay, it's a cyclic code. What do you mean by cyclic code? Cyclic code is a linear code. First of all, it's a linear code. Code is said to be cyclic if it is linear. Linear means it is subspace, right? Of some dimension, right? And second, any cyclic shift of code word is again a code word, right? So you take a vector x in C, shift it, cyclic shift, right? One bit right, and you see this is also a code word. It's a beautiful property, right? Take another code word, shift it, that is also again in the space. This property is there and should be linear. Let me take some examples. So essentially what I am saying that if C0, C1, Cn minus 1 belongs to C, this will imply that Cn minus 1, C0, Cn minus 2 belongs to C as well. This is a vector of length n. This is a vector of length n belongs to C. Its cyclic shift also belongs to C, right? So this is the property. Of course, C has to be linear first. Linear, number one. Number two, this property. You take any code word, shift it. It is also in the C. So this is an example. So this is a definition of cyclic code. let us take some examples here. If I take code 000 101 011 110, is it a cyclic code? Any idea? Is it a cyclic code? If I take 000, no matter how many times I shift, it will remain there, right? If I take 101, I shift it, I get 110, which is there. If I take 011, I shift it, I get 101, which is here. If I take the last vector 110, I shift 011, which is second vector, right? Everything is shift here. What property is left? So second property is satisfied. What about the first property? Is it a linear code? So that means it should be a subspace. There should be basis here, right? So is there a basis? Obviously, if you take any two vectors, so if you take this and this, sum them, what you are going to get? 1, 1, 0. Right? So you can take the middle two vectors as a basis vector and generate all four vectors, right? By taking lambda 1 times first vector and plus lambda 2 times second vector, right? So it's giving you all this, all the four vectors, right? So linear is there, linearity is there, shift property is there, right? So it's a cyclic code, right? These codes are very beautiful code actually, you know. So in the computer memory architecture, even when you download something from the internet, right? So there is something I know, I'm sure you might have heard about CRC check. Have you heard of CRC check? So that is using cyclic redundancy check, you know. It's kind of cyclic code which is used there, you know. So all these are very, very important things, you know. So now let me give you some more examples. One, two, three, four, 1, 0, 0, 1, 0. So question is it a cyclic code? Yes or no? No. Why? What is the problem? Is it a linear code? It's a linear code, right? Again, you take the middle two vectors and you can get all the four vectors, right? It's a linear code, no problem. What about the cyclic shift business? If I take 1001, I shift it, I will get 1100, which is not there, right? So this is not a cyclic code. Story ends or story begins. Now you see the beauty. What I'm going to do here, I'm going to interchange third and fourth bit. It 1010 0000 1010 0101 1111. What I have done? I have changed third and fourth bit, right? Interchange third and fourth bit. We are getting this. Now I ask the same question. Is it a cyclic code? Now it becomes cyclic code. No? Just check. Now it is a cyclic code. It is linear? Yes. And shift of everything is here. If you look at the vector 1010, you shift it 0101, which is here. If you shift this one, 1010, which is here. If you shift the last one, it will be there, and the first one will be there, right? So it's a cyclic code. Right? Something non-cyclic, you can make it cyclic by doing certain operations on the column side. That is possible sometime, right? So that's a beautiful thing. If I take this code, is this a cyclic code? Is this cyclic code? Why? If I take the vector 1, 1, 1, I shift it, it is there, right? Linearity is a problem, right? Zero vector should be there, right? Zero vector is missing. So it's not linear, right? So this is not a cyclic code. This was not a cyclic code, but this is a cyclic code. What about this vector? All zero vector. Is it a cyclic code? Huh? Yes, because shift is there, no problem. And singleton zero is always a space, it's a linear space, right? So it is a cyclic code, right? What about this? Lambda times 1, where FQ is a field with Q number of elements. I think you know what is FQ. Is this a cyclic code for any lambda in FQ? Obviously, because 0 is there, it's a, it's a linear space, right? Which is there. Linear code is fine. What about cyclicity? You will see that it is a cyclic code. You can verify. Right? What about this space here? If I look at whole space FQN, is it a cyclic code? FQN is a space anyway, n-dimensional vector space over FQ. FQ is a finite field with Q number of elements, right? So it's a linear space, no problem. Is it a cyclic code? Because it's all, no matter which code word you pick up, its cyclic shift will be there anyway, right? So this is also a cyclic code. Right? So now I think I will give you some idea about how to handle this cyclic codes actually. Have you done any course on numerical methods? No? So normally, anyway, so if you want to fit a curve somewhere, on certain points, what is the best way? Normally we fit spline. Spline is a kind of polynomial that you fit, give you a smooth approximation. Now, in a similar manner, actually, in fact, now what we here, all this machinery of generator matrix, parity check matrix, and so on is too much space consuming, right? But actually, we can use the powerful algebra of polynomials to handle the cyclic codes easily. So I will show you, give you some idea about how this is done, right? Basically, using polynomials, we can handle everything. Okay, so let me show you one. What we want here, that if C0, C1, Cn minus 1 is there, I assign here these bits as a polynomial. C0, C0 plus C1x plus C2x square Cn x raised to power n minus 1. And I call it as a polynomial Cx. So what we are doing, those bits I am mapping into a polynomial, right? Now you know that this connection, this is a beautiful observation, right? So bits I am mapping into a polynomial. Now what will happen to the whole space? We have Z2, 3 or whatever space. Every vector will correspond to some polynomial. Everything will be converted into a polynomial, right? And our linear space that we are looking at will also consist of a bunch of polynomials from that whole polynomial space, right? So depending upon the kind of modulo operation we are doing, and I think I will show you how the modulo operation is induced here. becomes, in terms of algebra, known as ideal. The linear space becomes ideal in the polynomial ring. Okay, so this is a beautiful connection actually. So you can see that. Let me show you. First of all, so we know that cyclic shift. I just one line I just write and then I'll finish. X times Cx is what? X times Cx. X means when you multiply Cx with X, what is happening? Every bit is shifting towards right? So X times Cx is what? So this reduces to C0 plus C1 X basically I would say that multiply. So what happens? C0x plus C1x square plus C2x cube plus Cn minus 1 x raised to power n, right? I multiply with x. Now we know that this is, going outside the space, right? We have only n bits. So, I mean, this, the degree of the polynomial is going, so what should be happen? This term, x raised to power n should be 1, right? Then only this is happen. Then this becomes, actually a shift, basically. So this is the condition that is coming us. So that means whenever we are doing any operation with these polynomials, once we map everything to the polynomials, when we are doing any operation with the polynomials, I have to keep in mind that whenever x raised to power n becomes, I should reduce it to 1. This we should keep in mind, right? While doing calculations. I think, so that's what we will show. I'll show you with examples, couple of examples. The beauty, how things are happening. So you will get some idea about the cyclic codes in the next class. Okay. Thank you. By the way, so I think now I think since the course number is fixed, probably we need to form a group for scribe writing, right? This is anyway is kind of everything about it. I mean, you may not be knowing, but I think this is very standard stuff. What I'm going to cover after 1 or 2 classes, that will be the core of the course. So that I would say that it's important to come to the class and make notes, because you have to make notes. Either you watch video or whatever, you have to make notes. It's one part of scribe notes, right? That you want you to submit, right? So keep an eye on that. Thank you.